Today we're going to be continuing to talk about the Z transform and stability. Let's go back to the Laplace transform here and realize that we said that x of s is defined by this integral, but we also said that that's the same as the Fourier transform of x of t times e to the minus sigma t, where sigma is the real part of s. Okay, so a question was asked on Piazza, and I thought I'd address it here. How do we get some intuition out of this? We've talked about what this Laplace transform is. I'm just going to reiterate this idea that you can think of the Laplace transform, it's two-dimensional, but you can think about each vertical slice of this thing, whoops, imaginary, each vertical slice being a Fourier transform. And they're all just laid side by side, infinitely many of them. It's a lot like the short time Fourier transform, the spectrogram you used in when doing Shazam, for example, or doing the MP3 encoding. But what we're laying together side by side are not Fourier transforms of different short time segments of the signal. It's the entire signal times a different exponential function. Okay, so we just have many different versions of the Fourier transform, each times a different exponential function, which means only some will converge and some won't. So there's some region of convergence, and that just means that when you multiply by these exponentials, you're not going to always get something that you can take a Fourier transform of. Only between a certain range will these actually be Fourier transforms, and they won't exist outside of that range. Okay, so really we're not going to be very interested in evaluating the Laplace transform anywhere other than the imaginary axis. If we really want to evaluate it, it's probably to get some frequency domain interpretation of it, and we have lots of intuition for the Fourier transform. So it's this imaginary axis where the Fourier transform lives. That's where we care to be able to sort of evaluate the value of the Laplace transform. So then you might say, why even have these other axes? You know, why have these other vertical lines that we care about? Well, you'll see by the end of the lecture today how we'll be able to use what we know about stability to make use of things other than just the Fourier transform part of this. Okay, so then we have a Z transform, right, which as we wrote, x of z is a sum okay, it's this which we can also say is the Fourier transform of xn times the absolute value of z to the n. Okay, so when I say it's that, I guess I should be a little more clear. I'm saying it was more clear when I did this in the previous lecture. What I mean by it's the Fourier transform of that, I mean if we substitute s equals sigma plus I 2 pi f, then we get this equivalence here. Okay, so if we let sigma be the real part of s, and we let 2 pi f be the imaginary part of s, then we just put sigma into this equation. We take a Fourier transform that gives us a function of f, which will correspond to the 2 pi f in s. Okay. Down here, what we mean is if we let z equal, let's say, a e to the I 2 pi f, okay, then we get this equivalence with the Fourier transform by the magnitude of z now is a. So we can put a to the n there. Okay, now you notice that one of the main differences between the form of the Laplace transform and the z transform is that here our parameters in the exponent in the Laplace transform, and here it's in the base. And so you can think about a substitution that the z transform is just the same as the Laplace transform, but it has with the sum instead of integral, but it has made this substitution that is z equals e to the s. So if you wrote out what you would have thought would be the discrete time Laplace transform, just by changing the integral to a sum, then the only real difference is that you have you've substituted e to the s with z. Okay, and if you think about that mapping of the space of S, taking e to the s, you get a mapping like the following. If this is the S space, and here's the z domain, then what you have is that vertical lines, for example, the imaginary axis here, map to the unit circle over here. Let's check that. So there's one. What we mean by that is the imaginary axis here is S equals I 2 pi f. Then that means that z equals e to the s equals e to the I 2 pi f. And the magnitude of e to the I 2 pi f is 1, right? And the phase of e to the I 2 pi f is what? What? So the magnitude is 1, and the phase is just 2 pi f. Okay, this is the polar notation for complex numbers. Magnitude of 1 is just implied out front, and you always have e to the I phase. All right, so in other words, points like this point here, which let's say you take I pi, that maps to this point right here. The origin maps to, this is just 0, maps to e to the 0. Okay, and what you get is that this imaginary axis actually wraps around that unit circle over and over. Okay, because if you look at, you follow along the imaginary axis and plug it through the e to the s function, you're going to get, of course, as you go from 0 to I pi, this path here follows this half of the circle. And then as you keep going, you just keep going around. Once you get up to 2 pi, to I 2 pi for s, you're back around to the origin here. And then you just keep going around and around. So this implies something about discrete time signals, that their Laplace, if you did the Laplace transform using this e to the s notation instead, they would be periodic vertically. Okay, and we see that just comes out when we map it over. We see that as you go around in circles, of course, you're going to get the same values over and over. What did we know about the Fourier transform of discrete time signals? They're periodic, right? And their period is, in frequency, their period is 1. Well, here what we've done is we've mapped these over here. If this is a frequency 0, s equals I pi corresponds to a frequency of a half. Okay, there's our equation, right? So frequency 0, frequency a quarter, frequency a half, frequency 3/4. Of course, that's also frequency minus a fourth, right? Here's frequency 1, frequency 1 1/4. Okay, so I guess what I'm saying here is in the z transform, if you let a equal 1, then this is just the Fourier transform of x. So the Fourier transform of x is equal to the z transform where a equals 1. And the z is just e to the I 2 pi f. Okay, so we did a graph, a three-dimensional graph of the Laplace transform last time to solidify our understanding that this imaginary axis, the values of the Laplace transform along the imaginary axis, are the Fourier transform. Right? Here what we have is, in the z transform, the values of the z transform around this circle is the Fourier transform. Okay. Okay, so then other vertical lines here, other Fourier transforms of exponentiated things, are going to be on other circles. Okay, so in other words, this equation right here says it all. If A is bigger, if the magnitude of z is bigger, that's another circle. Then we're taking a Fourier transform of x times some exponential. Okay, like I said, we're not generally going to care we're not going to care so much about the values of the z transform aside from this unit circle. All right, but we look at the whole thing because we care about the region of convergence, actually. Okay. So, just a moment. Hold on. All right. So, just like in the Laplace transform, we have regions of convergence. Okay, and in this case, they're always rings. Whoops. Defined by the absolute value of z being in some set. Okay, so in other words, we'll get things like example would be something like this. Here's the real part of z. Here's the imaginary part of z. And you might have a region of convergence that is like between two circles defined by absolute values of z. And it may only converge, the z transform may only converge in this set of z values. Okay? Now, like we talked about last time, if we have a right-sided signal, then we understand something about the z transform. Just as in the continuous case, if we have a right-sided signal, remember what that means, it's cut off to the left. Okay? Then the region of convergence has no outward boundary. Okay, so it wouldn't be cut off on the outside here. What was it for the Laplace transform? A right-sided signal had no what? What did we know about the region of convergence? Yeah, had no right boundary. So here, the right in the Laplace transform is sort of outward in the z space. All right. And then, of course, if it was left-sided, then the ROC has no inner boundary. Now, there's one catch. You can actually have a pole. You may have a pole at z equals 0. In other words, it may not be true that the region of convergence contains 0, even if it's left-sided. Okay, but it won't have any boundary greater than 0. In other words, if you may be missing, so in other words, if it was left-sided, it would go all the way into the origin. It may not actually have z equals 0 in the region, but it has everything up to it. Okay. Yeah, if it goes to exactly, it could blow up towards negative infinity in the Laplace domain. All right, and of course we had two-sided. Sorry, we'll skip two-sided. We had finite duration, which means it's both left-sided and right-sided. So, of course, the ROC is the whole space, or actually it's the whole space here. You can't have, well, it might not count. It might may be missing z equals 0. Okay. Otherwise, it's the whole space. So it's just similar to what we learned. We won't dwell on that too much. But we have also this notion of stability. We've already talked about stability for both discrete time and continuous time systems. What bounded input, bounded output stability means, and so forth. And we know it's sort of related to having a Fourier transform. At least if it's stable, it implies that there exists a Fourier transform. And what we get here is that if the imaginary axis, sorry, not the unit circle, we're in the z domain here, is in the region of convergence. Okay, so stability implies that the unit circle is in the region of convergence. Now, if the unit circle, just like the previous case, if it's in the interior of the ROC, then it implies it's stable. Okay, so if it's on the unit circle is on the boundary of the region of convergence, then it doesn't have to be stable. All right. Again, you could use the sink as your example there. Okay, so let's see. Okay, so let's look at some properties of the Laplace and Z transform that are going to be very useful. So so first of all, we have linearity. Right? So ax of t plus by of t, when you transform it with either Laplace or a Z transform, you just get ax of s plus by of s. Okay. But more importantly, we have a convolution property. That is that x of t convolved with y of t, if you take the Laplace transform of this in the Laplace domain, it is just the product. So actually, this is the key why this is going to be useful for us, just like the Fourier transform had this property. Okay. In fact, this property, a little bit of an aside, where this property comes from, well, another way to look at this property, either in the Fourier transform or the Laplace transform, is to realize that certain signals, if you have any LTI signal, so convolve with H there, that's LTI. Any LTI signal, if you put in, there are certain signals in that we call eigenfunctions, all right? And when you put them in, you get the same thing back out. Now, before, when we were looking at the Fourier transform, we already did this case. We said if e to the I 2 pi f goes into an LTI system, we could evaluate what comes out. We've done this in previous lectures. We could do it straight from the convolution integral. We could do it from all sorts of properties we know. And we know that we get h of f times e to the I 2 pi f, where this is the Fourier transform. Okay. And so you call this an eigenfunction because the same thing came out just with a constant multiplied by it. But it turns out that's actually true for a wider class of signals. We could also put in e to the just arbitrary. Oh, whoops, there's no t there. Should be t's. Okay. We could also put e to an arbitrary s of t, or in other words, I could say e to the sigma t times e to the I 2 pi ft. So we don't just need to look at complex exponentials that don't grow. We could allow them to grow in one direction or the other. And we would find that what comes out is still of the same form. It's just, now it's h of s. Of course, we would plug in s equals sigma plus I 2 pi f to figure out which s do we plug in here. E to the sigma t, e to the I 2 pi ft. So, in other words, this property of being an eigenfunction is more broad than just complex exponentials that don't grow. It works for ones that grow as well. And that's why we can generalize the Fourier transform to a Laplace transform and still have this wonderful property, this convolution property, okay, which is so useful for us. Now, the thing is, when you go to this wider class of functions, they're not orthonormal functions, so you don't get all of the same intuition that the Fourier transform gave. When you just look at this set of functions, they're orthonormal. And you get things like Parseval's theorem. Do you remember in your problem set what Parseval's property is? Can someone describe it? Yes, exactly. Energy or power, depending on whether you're looking at periodic things or not, are equal in the time domain or the frequency domain. So let's take energy, for example. The energy of a signal, we know you square the magnitude of the signal and integrate it. And if you do that same operation to the Fourier transform, you'll always get the same energy. That's very nice property. It lets you know you split up your signal but didn't somehow get more extra things in your new representation, right? And that works with the Fourier transform, and that really comes from the fact that this signal set is orthonormal. But when we look at this Laplace transform, now we have way more signals here. The Laplace transform is two-dimensional, and you don't get that same relationship. You can't do a two-dimensional integral over the Laplace transform and get the same energy. Okay, so, but anyway, this convolution property still works. Okay, how about we have this property. Again, this is one that you really became familiar with in your problem set more than the lecture. But if we take a derivative of x of t, and we take the Laplace transform, then what we get here is just s times x of s. Okay. If you remember, the Fourier transform property was this same thing, except we had I 2 pi f plugged in place of s. So there's a property. You can find it in the Fourier transform tables in the book, or go back to one of your early problem sets. And you'll see that for the Fourier transform, we get I 2 pi f times x of f. And here, just replace that with s. And for the integral as well. Since these are inverses, you just get this. However, in this case, the new region of convergence is whatever the region of convergence was for x of s. In addition, you need the real part. Now you have a pole, right? This introduces a pole at s equals 0. So the region of convergence, you have the real part of s must be greater than 0. You have that unioned intersect, with the region of convergence for x of s. Okay, we'll understand that a little bit better in a moment. Okay. Now we could have a time shift property. So we'll go ahead and do that here. And that is that x of t minus cap t. I'm just going to use, cap t. That Laplace transform of this, again, from our Fourier transform memory, we can probably guess that it is just e to the minus ts x of s. The reason I say you might have guessed that is because if you, again, plug in I 2 pi f for s, we already knew that a time delay was an e to the I 2 pi f times the time delay. Yes? Well, because this integrator is causal, the way it's defined here. There's going to be a pole, unless something cancels in x of s, there will likely be a pole at s equals 0, which means the region of convergence, remember, is going to be, the poles are going to form boundaries of the region of convergence. So it has to go one way or the other, and because it's causal, it's going to go to the right. Yeah. Okay. Now, notice something about this one. We have a time shift property. This here, well, at least the new term that we've multiplied on because of this time shift, it's not rational. Okay. In the previous lecture, we said we're going to focus on rational transfer functions, which means we're not actually going to care about this case much in continuous time, okay, about time delays. However, in discrete time, that same property holds, except in discrete time, the time shift property is going to be this, x of n minus a time shift. Now it's going to be an integer time shift in discrete time. So I'll just use a little k. We're used to k's being integers. That, when we do the z transform, whoops, z looks like L. Those all look like L, like z's. Okay, that looks better. How about that? Yeah, I'm going to erase these. Okay. Now, here you're going to get z to the negative k x of z. You see how this is just a substitution of take e to the s equals z. Okay, so it's the same property. However, in this case, this is going to show up in the types of cases we're interested in because this is rational in z. In fact, one of the reasons why it's important that the z transform is defined as it is because many important z transforms that we look at will be rational with the correct definition of the z transform that we've learned. Okay, so in other words, these time delays will be cases we care a lot about in discrete time. Okay. So now let's look at something here. What is next? right. Okay, let's do an example of a z transform. Let's let x of n equal just two delta functions. Okay. Now, by linearity, we can just take the z transform of each of these separately. So we get x of z equals, what's the z transform of delta of n? Well, we could plug it right into our z transform integral sum. What do we get? Anyone? So the z transform sum is up here. Here it is. Oh, are you doing the whole thing? Both of these combined? No. Wait, let's see. So put delta n in here and use the sifting property. It's just going to be 1. Okay? Because delta n only is 1 at time 0 and nothing else. And at time 0, this is just 1. Okay, so this is 1 minus 2 times, what's the Fourier transform of that one? Well, you can plug it into the sum, just like you did. Or you can use the time shift property. Either one, whichever one's faster. What's the answer going to be? They're both about equally fast. What? Z to the negative 1. Which way did you go, the time shift property or the sum? Time shift. Okay, so this was delayed by 1. So k is 1. So it's z to the negative 1 times x of z was 1. Okay, so so there's a z transform. Now, let's write this in the, notice that, is this a rational z transform or not? Okay, it is rational, and to make it obvious that it's rational, we might want to look at, we might want to make it into a ratio where all the z's have positive exponents. So this equals z minus 2 over z. Okay, obviously it's rational. Okay, now we know, in the Laplace transform we had rules about the region of convergence for rational functions, and we have the same ones here. For rational z transforms. Okay, the poles are at the boundaries of the region of convergence. And the boundaries are circles, as we already said. That's always true. And we know that the ROC is connected. I'll put these in parentheses because these last two things are true for any z transform. But that top one is what's important about the rational z transforms. You just need to know where the poles are, and you know now what the region of convergence is. Okay, or at least you know the options for regions of convergence. For example, they might be, you might have something like this. You might have, here's one. Let's draw the unit circle just to give us some bearings. And you might have poles that are here and here, and you might have a pole out here, and you might have zeros here and here. Okay? And the possible regions of convergence for these poles and zeros are found by putting circles where each of the poles are. You ignore the zeros. Those don't affect the region of convergence. And there are three possible regions of convergence for this rational Z transform. You could have one that's out here. You could have one that's between. And you can have one that's inside. And what can we say about these three situations? The green one, what do we know about the signal that would have that Z transform? Yes, so it's right-sided. Okay, is it stable? It's not stable, and that was determined because the unit circle is not in that region of convergence. So the Fourier transform would not work for that signal. It's a signal that's growing to the right. Okay, and what about the purple? We know that, what about this? Let's do something. Okay, yes. So, oops. Okay, so this is what we might say two-sided. Okay, and it's is it stable? Yes. Is stable. All right, and lastly we have this blue one, which is left-sided and not stable. So three possible signals could have this rational function as its Z transform. Yes? Two-sided should mean that, but it actually just doesn't mean anything. But people say it when they want it to mean that it is not left-sided and not right-sided. So you should think of it as something that goes on forever in both directions. What was that? Yes. So purple will be. So this is mathematically. This is what you should be thinking. This is the important part. It's neither. If it was right-sided, then it couldn't have an outward boundary. So it's not right-sided. If it was left-sided, it couldn't have an inward boundary. So it's not neither of those. Which means mathematically, it's not bounded to the forward in time or backward in time to be in some finite duration. In other words, it has tails that go on in both directions infinitely. We know that much about it. People will often call that two-sided because you're thinking it goes in two sides. Unfortunately, because of the way right-sided is mathematically defined, it doesn't actually mean it's right-sided and left-sided. But you get the idea. When we say two-sided, think of something going off in both directions like this. Right? I know it's a little bit confusing, but you get used to it pretty quick. So, good. So we know that there is no finite duration signal that could have these poles and zeros. But why don't we go up to the example we were working out here? Let's do the poles and zeros here because it's rational, right? So we can do the poles and zeros for this thing. Well, where are they? How many poles and how many zeros? So the order of the polynomials is first order in the numerator and denominator. So there's one pole and one zero. So where are they? Where's the zero? The numerator's root. 2. So here's 1, here's 2, and we have a 0 right there. Okay. Now, where is the pole? Yes, we have a pole right there. Okay. So where are the possible regions of convergence? Well, there's only one possible region of convergence. It's the whole space except for the origin. We'll just call that the whole thing. Okay, of course, the pole at the origin can't be actually, it means it doesn't converge, but basically the whole space. So that's why we had that property for finite duration up here. We said finite duration means the ROC is the whole space, maybe missing z equals 0. And this is exactly showing that. Nowhere. It is a possibility, but not for finite duration in this case. Okay, so if it's finite duration, then it has to converge everywhere except maybe at the origin. In continuous time, you could have had some vertical asymptote, but you don't get that in discrete time. Yeah. Okay. So okay. Yes. Well, except we know it's finite duration. If that would be enough to know that it has to converge. Yeah. So okay. There are a few transforms that you should just know, important z transforms to know, because I already said that you're not going to be using the inverse Laplace or z transform integrals for what we're doing. So let's just look at some cases here. If you have, so for Laplace, we have okay, so we have this e to the minus at u of t. Okay, that transforms over to 1 over s plus a. All right, with the real part of a, s has to be greater than the real part of a. Okay, we did this as an example. And we also have something like this, negative e to the negative at u of t goes to the same thing, but with the opposite region of convergence. Okay. We also have something like this, t to the k, e to the minus at u of t. So this is a polynomial times an exponential. Oh, whoops. That should be minus t. That's what it is. U of minus t. So one of these is in the right side of t, and one of them exists for negative t. Okay, so this is going to be k factorial over s plus a to the k. All right, and again, it's got the real part of s has to be greater than the real part of a, and there's going to be another one for the same thing with the other region of convergence. But I just mentioned this one to show. Notice a couple of things here. These are all rational. Okay. And notice that, of course, the k is just a constant here. So don't get thrown off by that k factorial. Also notice that this one has a second order pole. By that I mean 2 poles in one place. So you can have multiple poles and zeros in the exact same location. All right, and in a pole zero plot, you might put a number next to it to indicate how many. Oh, sorry. Yeah, kth order. See, my mind is in different places. All right. So it's a kth order pole. So for example, we would be interested in just t e to the negative at. Okay. Then that would be a second order pole. Wait, hold on. I'm off here. K plus 1? Great. Let me... You want to look that up for me, Sai? I think maybe it's K plus 1. It's not. Exactly. Yeah. So I think this might be right. Okay, so if K was 1, you'd have a second order pole and so forth. So we have some sense of what it means in the time domain. If you have multiple poles in the same location in the Laplace domain, that corresponds to something of the form of polynomial times an exponential. So this is it? Okay, good. Let's do some Z transforms over here. Some that you'll want to remember. We already saw delta n goes to 1. And we saw that delta n minus k goes to z to the minus k. Okay, so that's just a reminder. But we also have something like this. A to the n u of n goes to 1 over 1 minus a z inverse, where the absolute value of z has to be greater than the absolute value of a. Okay. And we have something else, negative a to the n u of minus n minus 1. This goes to the same thing, but with the other region of convergence. Okay, so it's maybe it will throw you off a little bit there to look at, why is the minus n minus 1? And what is the u of negative n minus 1? Where obviously it has a negative n in there, so it's a indicator function that is 1 for all n up to a certain point, and then it's 0. What's that point? The last value where u of negative n minus 1 equals 1. It's actually at n equals negative 1. So in other words, it's going to only, the signal will only live on strictly negative values of n, not including n equals 0. If this was a u of negative n, it would be 1 for all values of n less than or equal to 0. This is 1 for all values of n strictly less than 0. Okay. And you also can get a second order pole with something that looks like n a to the n u of n. And in this case, gosh, I have to admit, I tried to print out my notes today and the printer was not working for me. So that's why I'm not exactly remembering the formulas. Maybe you can look that one up too, Sai. I know the denominator is this squared. And we still have this greater than a. And the last, and we'll check what the numerator is. Maybe it's 1. I don't know. And then you also have something like this. And this has the same formula, but it's for z less than a. Okay. So we'll get back to see if that numerator is actually 1 or not. Yeah, we'll check that later. Okay, so let's look at one of these simple ones that I have here, like a to the n u of n, and let's plot the poles and zeros. Okay, so if that's x of n, then x of z, we already saw, is 1 over 1 minus a z inverse. Okay, but to plot poles and zeros, it'll be helpful for us, again, to get everything with positive powers, z's with, polynomials with non-negative powers, right? So let's multiply the top and bottom by z, and we get z over z minus a. All right, so we just did a pole and zero, so this should be easy. Where is the 0 here? Let me put 1 there. Where's the 0? What was that? Okay. All right, and where's the pole? Z equals A. So A could be complex, so I'll put it up here. Pole. This is at Z equals A. Okay, so what that means is there's 2 possible regions of convergence. One of them, and this pole is at the boundary of them both. Right? And so we get exactly what we had up here. We have 2 possible regions of convergence. We've got the one where absolute value of z is bigger than a, that would be the outside, that would be the right-sided one. And the one where it's less than a, that would be the left-sided one. And of course, the 2 signals that we know give this are right-sided and left-sided. Okay. Okay, what about causality? Because, again, causal is going to be important to us if we're implementing something in real time. Yes? What'd you say? Yes. That is a circle. Does it look like an oval? Oh, you know what? I think it squishes a little bit vertically. Looks more like a circle here. Okay. Okay. We have something really kind of fun in the Z-transform domain. That is, if something is right-sided, let's say a rational. So for rational Z-transforms, then right-sided implies causal. Remember, causal is a stronger statement than right-sided, right? Causal is right-sided. Let me make sure I'm not losing anyone here. If the impulse response of a system is causal, that means that it is 0 for negative values of time. Okay, so the Z-transform of, so that's a right-sided impulse response. The causal system has a right-sided impulse response, but just because the impulse response is right-sided doesn't mean it has to be causal, right? It could start at a negative value of time. So what we have here is it implies causal if and only if the number of zeros is less than or equal to the number of poles. Okay, now this is maybe seems kind of bizarre because in the Laplace transform, for a rational Laplace transform, right-sided and causal were always the same. You always have that right-sided implies causal. So an example of a can someone think of an example of a right-sided, okay, first of all, let's come up with a right-sided non-causal signal. Okay, non-causal impulse response. Just a very simple one in discrete time. Maybe the simplest one you can think of. We can work it out. There you go. Let's do x of n equals delta of n plus 1. So this is a delta function that occurs at time -1. If this was the impulse response of your system, then what comes out would be what went in advanced in time, it would be a prediction of what goes in, right? It would always come out one moment earlier than it went in. It is right-sided. Even though it's not causal, it's right-sided because remember, right-sided just means that there's some left boundary. It doesn't mean that left boundary has to be positive. Okay, so this is right-sided, but it's not causal. So what is the impulse? What is the z transform? X of z equals z. Okay, so then number of zeros equals 1. Number of poles equals 0. Okay, so there we see that it didn't obey this rule, and that's always going to happen. Whenever you have a right-sided signal that starts at negative points in time, it's actually easy to verify because what happens is you've got a sum of x of n, z to the negative n, right? And if x of some negative value, x of n is not 0 for some n less than or equal to 0, then this term is going to be something like, let's say, just pick an arbitrary k. I'll use a different letter. Pick an arbitrary k less than 0, strictly less than 0. And say that x of k is non-zero. Then you're going to get x of k, z to the negative k, plus the rest of the sum. Right? X not equal to k. Now even if that rest of the sum what I'm trying to show here is that this term here, when you combine all these terms as rational functions, this is going to force the order of the denominator to be larger than, the order of the numerator will always be larger, even when you add these two terms together. Okay, anyway, that was just for your curiosity. So we have this relationship between right-sided and causal. Okay. So now for the fun part of how to use this stuff. So we've done all the nitty-gritty details. Let's actually go use this to do something kind of cool. First of all, what happens if two systems are cascaded? Okay, so what I mean by that is you have an input, you have one system. We'll call this thing, it's a convolution with an h of, or actually let's just say you have one LTI system, which we'll call h. And then what comes out goes into another LTI system, which we'll call g. All right. So the relationship between x of t and y of t here, okay, is going to be linear time invariant, and let's try to characterize its poles and zeros. Okay, suppose these have rational Laplace transforms. Okay, so we know that in general, what comes out here, if we take the Laplace transform of this and call it x of s, what comes out here will be h of s times x of s. Whoops. Because of the convolution property. Right? And what comes out here then will be h of s times g of s times x of s. So the entire system, h of s over x of s is the transfer function of the system, right? So this is the, looking at this entire block as one system. It's one new LTI system whose, where the Laplace transform of the impulse response is exactly, it has to be this ratio of h of y of s divided by x of s. This is just a rewriting of the Laplace of convolution rule, right? If x of s times the Laplace transform, if y of s equals x of s times the Laplace transform of your system. So if you rewrite this, take the x underneath the y, you know the Laplace transform of any system is this ratio of y of s to x of s. So the transfer function of your system. And what's it going to be here? It's just going to be the product, right, of the two systems. So what we get is that when you cascade two systems together, the new Laplace transform is just the product of the original two. So what can we say about this? The poles and zeros. What can we say about the poles and zeros of the product? Yes, exactly. You combine poles and zeros. Okay. Now, what that means is you also have to take into account that a pole can cancel a zero if they're in the same place. So a pole from one system in the same place as a zero from another system can cancel. Okay. Yeah. Yep. So if one system has a zero exactly where the other one has a pole, then when you cascade them, there's no pole there anymore. Okay. So basically, then we'd want to look at maybe regions of convergence, right? You just eliminate it from your equation because it'll always. I mean, if you have a rational function where the numerator and denominator cancel, yeah. A second order pole counts as two poles in the same place. So if there was a zero that landed on a second order pole, it would become a first order pole, right? So one of the poles and the zeros would cancel. All right, so the region of convergence for this new system is going to be the intersection of the two ROCs. However, if a poles, remember the regions of convergence are defined by the poles. If a pole cancels, then the region of convergence expands to the next pole. Okay, so what we're saying here is it's possible to take an unstable system. All right. So an unstable system, we're doing Laplace transforms here. Everything we're learning right now applies to Z transforms as well. Okay. So suppose you have a Laplace transform that has a pole right here. So here's one, has a pole there, it has a, I'll put some zeros. And you have another, so that's the poles and zeros for H. And you have another system G. Or let's say this is for G, just because it'll fit my story better. And you have another system H that you put in front of it that has a pole here and a zero here. Okay? And let's suppose these systems are both causal. Then I would like to know, first of all, so we have H of, or S is the green one, and G of S is the black one. Is H of S by itself, is it stable? Well, we're assuming they're causal, both of them. So you're saying it depends on, so is H of S stable? Yes, and why is it stable? Yes, because the imaginary axis is included in the region of convergence. In fact, we know this general rule for causal systems, the poles all need to be in the left half plane, and then we're good for stability. Okay, is G stable? No. I see some no's. Because of this pole right here is going to cause, the region of convergence being a causal system will be to the right. It does not contain the imaginary axis. So it's unstable. So if we looked at the impulse response of this system G that has those poles and zeros, it's going to be something that you tap it with the delta function and it grows and grows and grows and is unstable in our definition of stable, right? And what we're basically saying is, now when we combine these, where are the new poles and zeros? How many poles does it have? How many zeros does it have after we combine it? So it just has one pole because this gets annihilated, right? And it has two zeros. And what's the region of convergence of the combined system? Well, since there's only one pole, it has to either be to the right or left. And I've said that when you cascade them, you take the intersection of both regions of convergence were to the right. So the resulting thing is also to the right. It's also a causal system in the end. Okay, so you end up with, so the cascade of these two things, is it stable? It is stable. So you could view this as one way to control G. G is some actual physical system. It's like a rocket or something that you're trying to steer. And you don't want little bits of noise or little bit control signals at the input causing it to spin out of control, right? You want the response from your input to the output to be stable. So since G is not stable, you could put some control system in front of G that cancels that pole. Okay? And the resulting system is stable. Okay, so this is the whole magic. Oh, well, we'll see. It gets more fun than this. This was just one example. This is not how you would really build a control system. But anyway, this is the kind of fun that you can do with the Laplace transform to figure out whether a system's stable or not and how to make it stable. Okay, can anyone think of an idea, or maybe it's in your problem set that you are asked to think of reasons why this might not be great. But can anyone think of an idea why this would not be the best way to build a control system? Because you could look for the poles that are causing your system to be unstable, design something that has zeros right there and cancels those poles. Yeah? Yeah. If you're not exact, a pole next to a zero is still unstable. They have to be exactly canceling, and it's very hard to build exact devices, right, to do this. So there are better ways of doing control other than this. This would be called an open loop control. There's no feedback here. If we include feedback, we'll be able to do really cool control. Okay, let me show you that we can solve. So remember that we kind of motivated some of this by looking at a circuit a few lectures ago, and we said with the Fourier transform we can take these differential equations that are implied by the circuit, we can solve them. let me show you that formally you can actually solve differential equations of a certain type very easily with the Laplace transform. So since we're short on time, I'll do the block diagrams that we solve with these differential equations in the next lecture. But for now, suppose you have something of this form. Actually, I will do a block diagram because I think it motivates it better. So we'll talk about how to interpret these block diagrams. I think they're pretty natural. That's an integral sign. Okay. Let's do something like this. Okay. What I've got here, the arrows are pointing like directions that a signal goes. So x of t comes into this adder. This adder is going to take y of t and add it to x of t. All right? And then the 5 there means it gets multiplied by 5. So it goes through some sort of amplifier. Scales it up by a factor of 5. And then it comes in here, and this block just takes an integral. In other words, it just accumulates the input signal, doing an integral from negative infinity to t. Okay? And spits that out at the output. So this would be the type we might be able to build an integrator in a circuit using amplifiers and stuff. And so we might want to know what happens if I hook up feedback like this. So this will be our simplest components we're going to use for a block diagram to design some sort of continuous time system. And we want to see what does it do. So first of all, how do you handle feedback and stuff like that? Well, it's actually pretty easy. Just give labels to each signal at each point along this chain. So anything along the same line has to be the same signal. So that means this here is y of t. And this coming right out of that adder is just x of t plus y of t. If it helps, you can give it a new name. Name it as a new signal. But it equals x of t plus y of t. So on this side of that amplifier, we have 5 x of t plus y of t. And out of this integrator, we have the integral from negative infinity to t of 5 x of tau plus y of tau d tau. And now we have an equation. Because this, what come out there, equals y of t. Okay, so this block diagram implies a certain equation. It implies that y of t equals the integral of 5x of tau plus y of tau d tau. And this is a differential equation. Okay. Let's write it in another notation. Let's take derivatives of both sides. Y prime equals 5 x of t plus y of t. Okay, so sometimes you might want to write a differential equation as y in terms of everything else, and you would have this. Y equals negative x of t plus 1/5 y prime of t, and that might look like a standard differential equation to you. And I'm sure you could solve this immediately, many of you, because this is a differential equation that's not too difficult. But we will actually use a Laplace, show that any differential equation of this form. Let me write a general form of what's called a constant coefficient linear differential equation. Okay, so that would be of this form. We have a sum of, let me just get it correctly here. We have a sum of some coefficients, ak, times the kth derivative of y of t, okay, equals a sum of some other constants times kth derivatives of x of t. Okay, So this would be a general form of a differential equation. You have some of these going from k equals 0 to some number m, and m would be the order of this differential equation. Okay. Now the reason these are going to be simple to solve with the Laplace transform is from our rule, and that is the Laplace transform says that this is just that the sum, by linearity, we take the Laplace transform in, and we get, what's the Laplace transform of the kth derivative of y of t? Yes, s to the k, y of s. And what is, and then this over here, same thing. And look how simple this becomes. B to the k, sk, y of s, x of s. It's so simple because now we can factor out the y and the s. So the y and the x, and we get that y of s over x of s. Remember, that's our transfer function for any system. Y of s over x of s. That is just the sum of the bk's, s to the k, over the sum of the ak's, s to the k, and this is rational. So immediately, with no difficulty at all, we can take a differential equation of this form, and we could figure out its Laplace transform. And if we factor the numerator and denominator to get poles and zeros, we actually know a ton about this. We know if it's stable. Okay, we can, well, we have to know something about causality, but when I draw a block diagram, I'm implying causality. So if we know it's causal, then we know whether it's stable or not. We know, based on the poles and zeros, what the Fourier transform is, because we just look at the imaginary axis, and we can do distances to poles and distances to zeros to figure out the magnitude of the Fourier transform. So immediately we know a ton of stuff about such a system using this property. So we'll get back to that next time.